Right. So now I want to derive for you the other situation, whereas this is for small particles. So let us do that. So for small particles, this is of course called the Rayleigh limit, wherein the size of the particle is much smaller than lambda, and the Rayleigh scattering is the most dominant scattering that happens at this for the scale. You know that the sky is blue because of Rayleigh scattering, and indeed this is the kind of limit that one is talking about. All right, so now let's look at the force exerted on a charge, right? Then we will come back to a small particle. So the force is given by a charge is Q, the electric field associated with the electromagnetic wave is E. Similarly, if the velocity with which the particle is moving x by dt, and cross it with the B field. Right, this is the kind of force which is experienced by a charge which is moving. Right, now the charge is Q and its position is given by x. Right, now remember that once I have a dielectric particle, what I'm going to generate because of my electric field is basically a dipole. So if I have a dipole, one is asking what is the force on a dipole. So once you have the dipole, one is asking what is the force on the dipole. So imagine that a charge Q is at the location x1 and minus Q is at the location x2. And for this situation, I'm going to write down the force. So the force F is Q times E1, which is the electric field at the location of the charge 1, which of course is a function of x, y, and z. And you have minus Q, so that's minus the electric field at the location 2, x, y, z. Then you have, of course, the change in the locations, which is x1 minus so because the negative signs are all coming because of the negative charge which is there, and I have to cross it with the B field. Right, this is my total force. Now I know a few things. That is, the field at the location 2 can always be Taylor expanded about the field at location 1. So I'm using Taylor expansion. What I'm going to do is I'm writing down E2 in terms of E1. So which can be Taylor expansion. So this is approximately, it's E1, right? Which is a function of x, y, z plus x2 minus x1 dotted with the gradient of E1, right? This is the object I need to operate on E1, and so on and so forth. So I'm retaining only the first order term because that is the most significant. So I can write down again, I can come back to my force, which simply happens to be Q times. So I will not retain these XYZ, which is all understood as so. This is E1 plus this is now x1 minus x2. The change of sign has happened dotted with gradient operating on, let's just E, plus d by dt of again the same quantity, which is x1 minus x2, and you have crossed it with the B field. Now you will quickly recall the definition of the dipole, where it is simply the dipole moment is given by q times x1 minus x2, and then so I can basically write this out as that my p dot del acting on E plus this is dp by dt crossed with b. So this is what my force is. Now I know a few things, that my dipole moment P is related to the applied field itself through the polarizability alpha. So if I put that in back, what I get is alpha times E dot del acting on E dE by dt cross B. So you see that now I can do a little bit of vector algebra. So just a few more steps, and you would, so let me use another ink for the vector algebra. I know this for a fact, that my E dot del operating on E can be written as a gradient of E square. This is just coming from vector algebra, minus E cross del cross E. Right? So this basically comes from vector algebra. So you see that I can write down my force again. Let me get back to my force in the blue. So my force just happens to be alpha, which is a polarizability, times, so you have half gradient of E square minus E cross del cross E plus dou E by dou T cross B, the old term. Now I clearly recognize that my del cross E from the Maxwell's equation is simply minus dou B by dou T. So putting that, I would say that what we get back is our full expression, which is half gradient E square plus dou by dou T of E cross B. You will clearly recognize that this quantity by mu naught is basically the Poynting vector. This first notion is certainly is what is called as the gradient force, and this second term is basically the scattering force. All right. Other important thing to recognize that if there is no fluctuations, then you see that the second term actually goes to 0, and hence the dominant force will be only the gradient force in the absence of fluctuations in the electromagnetic field. Of course, if it is a time varying field, then of course scattering force does come into play. If I have a spherical particle, then in the Rayleigh limit, one can actually calculate this. So this F gradient, please don't try to remember this formula, but I'm just giving it so that you can you appreciate the way it is done. So for the spherical particle, one can write down the gradient force in this manner, right? So the gradient force is basically half alpha being the polarizability times the gradient of E square. So this is what you get, and this is gradient times the intensity, which is a function of R, right? On the other hand, you have remember that this ratio, this M is a ratio between the refractive indices of the particle and the medium. A is the size of the particle, and N naught is the refractive index of the particle, N1 being the refractive index of the medium. And in the scattering force, what you get is K, which is 2 pi over lambda of the incoming beam, and this is related to the intensity itself along the direction of propagation of light. So, right, these are the two forces that one can basically get. Now, just a small note. So, in particularly in biology, so what people have done is basically use something called the Gauss beams, Gaussian beams. These are basically the same Gaussian beam solutions, but wherein you have a vortex, okay, or what you have is a center which is where the phase is ill-defined. Okay, so there is a phase singularity at the center, and you have these beams which look like a donut shaped beams, and these beams carry a definite orbital angular momentum. I will not get into these beams per se, but basically what they carry, because they carry an orbital angular momentum, they actually impart this on scattering, they impart this angular momentum to the particles about which are from which they are getting scattered, and these particles can themselves rotate. So there are multiple advantages of such a beam. One is that one can, because at the center of the beam is dark, one can actually trap now absorbing particles. So and because the intensity is very low already, you can trap the particles at this center which is dark, and thus play around with biological samples which might be weakly absorbing. The other important thing is that if there is a structure uh, associated with the particle, then you see that the way the particle rotates itself can be used, can be studied by utilizing these Gauss beams, or the LG beams, popularly known as, to basically rotate and play around with these particles. The important thing is that there has been, for example, uh, a very nice application of this, which is, for example, to detect malaria. So you see that the red blood cells actually get infected by the malarial parasite, and the rotation of these red blood cells actually changes because of this infection, and which can easily be studied by the Gauss beams. So it's used as a tool for quickly diagnosing whether you are actually suffering from malaria or not. So you see that it's a very promising set of applications. All have come about because of lasers. The idea is that in the laser, one is able to get a specific spatial mode, okay, uh, and basically retain the coherence across the whole beam, focus it down uh, uh, to a very narrow spot, because it's a single mode of the laser, and so on and so forth, gives you tremendous control over the spatial and temporal aspects of the beam. And that is why lasers uh, are used in many of these applications, with an appropriate selection of the mode in which the laser is emitting. All right, so this is in short the summary of the issues related to optical tweezers. I'll give you a nice reference of a nice article by Arthur Ashkin, and this is something that you should follow it in case you are further interested in this. It has got some very nice pictures, and you can get some deep understanding of how. So this is in the Proceedings of the National Academy of Sciences, PNAS. It has sort of a history as well as important physics aspects of the optical tweezers. All right. Thank you very much.